Okay, this is the third kinematics simulations. This will be based on the chapter 4 of our textbook. So please refer to textbook for the detail of geometry. I'm going to start with the new assembly. Base, block, connection rod, and crank. I'll fix the base first. Then using the manipulation functions, I'm going to start pulling up so that we can easily connect, add in a constraint. Connection rod and crank. And crank. Alright, I'm going to start with the base. So coincident. So base edge, block edge, coincident, top of a base, bottom of a base. Coincident between axis to axis overhaul and plane. Come to this point, axis, plane, and plane. Last, axis, plane, and plane. So I added you look at the constraint, fix the base, then we have 1, 2, 3, 4, 5, 6, 7, 8 coins then being edited between edges or plane. So if I update it, it should be in positions. And then now we are ready to move on to the kinematics. And then we're gonna go to the kinematics. This is a markup, kinematics. And as you can see, the all constraint is already updated. So let me take this now. So we're gonna start with creating the joint, but before that, we have to fix the part first. In the process of doing it, it will ask to create a mechanism. So start with the fixing new mechanism. I'm gonna name it mechanism 1. Then go to base to fix, and you can see which part being fixed. So we're gonna have a revolute joint here. Revolute joint here. This one can be either revolute joint or cylindrical joint, and we're gonna have a prismatic joint there. So let's start with the prismatic joint. Prismatic joint, if you rotate it slightly, again, we are trying to access to those edges. So edges of block. Let's see whether I can get it. There we go. Edges of a block as a line 1, and edges of a base as a line 2. So now I'm trying to get the plane, which is the bottom of a block, so I'm going to hide the base temporarily. Then bottom. Then if I go to hidden place, then I can access to top of the base as a plane 2. Say okay. Then you can see prismatic joint being created. So I'm going to hide it and show. So I can go to the modeling space. Then I'm going to continue to creating the joint. Okay, the first one, I'm going to have a revolute joint. Revolute. In same sequence, I'm going to have axis and axis of connection rod. There we go. And plane and plane. So they aligned it up. Good. So I got the revolute 2. Another revolute joint I'm going to create in this side. In axis and axis, plane, plane. Then because of the mechanism now, since this is a fixed depth and another fixed depth, there's no changes allowed. So either revolute join here or cylindrical join here doesn't really matter now. So I'm gonna, just for the exercise purpose, I'm gonna have a cylindrical joint. In that case, you are asked to pick 2 axes lined up each other, simply able to rotate each other. So axis of this and axis of this. And now, as you can see, with the one prismatic joint here, revolute joint, and cylindrical joint, we have only 1 degree of freedom. So in this case, the simulation we're trying to do is by rotating crank, we want to see how this cube is react. So we're going to add a sensor, maybe this corner, and track the speed and acceleration and actual travel distance. So we're going to take over this 1 degree of freedom of this mechanism as our command. So in this case, our driving mechanism will be this revolute joint of this crank, which will be revolute 3. So double click. So again, we're going to make it 1 perfect rotation. So we're going to angle driven from 0 degree to 360 degrees. So actually it shows the direction of the rotations as you move mouse nearby those rotations. So if your intention was rotating the other direction, by simply click the arrow here, you can change the direction of rotation. So I will keep this direction counterclockwise. And as soon as say OK, because of a 1 degree of freedom will be taken by this command, then 0 degree of freedom will turn into the 0. That moment, the CATiA will let you know that this mechanism can be simulated. There we go. So now we can add the law, how quickly we want to rotate it. So by adding formula for the mechanism, for the angle, how quickly would you like to rotate it? So you can say maybe 660 degree will be rotated with a speed of 1 second, maybe, and multiply by your kinematics time, so that those units are homogeneous to each other. Say OK. So the formula has been edited. Then we can add the sensor, maybe this corner. So we're gonna have a reference as our base. So everything will be based on the 0 point of our base. So maybe I can put it right. Okay, put the base as a reference. Then I can put the sensor, actually one of the vertex there. So point of selection will be right there. And we're gonna rely on just main axis system of a base in this case. So the law is there, the sensor is there, so ready to simulate it. So I'm gonna simulate with the law. Activate the sensor. In this case, I'm gonna track back and forth in x direction. So x vertex, x linear speed, x accelerations. I think that's all I need now. So if you want, again, as you can see, there are some other the parameters you can actually track it. Then confirm of those parameters you are tracking. So right now, based on your base part, your sensor is now in negative direction, minus 211.118 millimeter away. Then initial speed we already got 0.159 and so on, and accelerations. Then change the history. Then if I start simulating, we'll be able to see the record of those data. For these cases, since we are making the 1 second as 1 revolution, let me just simulate only 1 second. So change the time for 1 second. Then I will track down is a 200 point, should be plenty enough. Then once I simulate it as a crank rotator perfect 1 rotation, which is 1 simulation second, then we got the result. So time, which was 1 second divided by 200, is there. So you can see the actual angle changes. And sensors, which one is it? And there's a value for the x location, x speed, and x accelerations. Based on that, you can track the graph. Right now, acceleration showing in x direction. You may be a little bit surprised with the shape. And here's the speed, and here's the actual distance changes. If you want, you can also, of course, export those values as an Excel file, and you can use for the later for other process as well too. Well, that concludes the simulation of this case.